Streaming is on. And then we change the display to basically it's 720p as a resolution. So we apply that. Okay, everything is good. Record is on. All right. So the first thing we need to do is to go over the homework assignment, the cousins program. So we'll go ahead. I'm gonna close the door, just because it's letting in a lot of light and it's, you know, affecting the contrast on the screen. There you go. All right. All right. So we'll go ahead and start with the program. I got it done already on this particular tab, but instead of just showing you the solution, I want to show you how I got it done. Okay. So the way I got it done is to look up definitions of cousins. Okay. Like what is a second cousin, what is a third cousin, and so on. And the one that I found that was most useful was the definition of third cousin. So when you look at the definition of the third cousin, you can see how it's making use of the definition of second cousin. Is that okay? So that means if this is n, if third is n, then second is n minus 1. I have just found the recursive relationship when it comes to defining your cousins. Is that okay? So that is the first part that I need to understand. The other part is pretty easy, okay? Ones, is the same generation as a child of, okay? And then we are looking at the parents of this child and the parent of one being second cousins. So we just need to establish parent of one, this guy here, and parent of this thing here, and make sure that those parents are second cousins. Is that okay? So that is the key. All right. So I will show you, as I type, the program, but I'm not going to show you the final answer just yet, because that would be boring. So instead of doing that, I'm going to work on this, piece by piece. So using mousepad, I'm now, going to summarize what we have just learned from the definition of third cousin. So now we can say cousin. Was it cousin or cousins? Cousins. Okay, plural. Okay, there we go. So we have x, y, and z. Okay, only if. Okay, so we need to establish parenthood between x and y. So now we have to say, okay, find me a parent of x. So that would be x1. So x1 is the parent of x. And find me a parent of y. And we call that person y1. Okay. So these two clauses will basically find, a parent, x1 of x, find a parent y1 of y. So x1, y1 are using the existential quantifier. Just find me one, okay? I don't know how many there are, but just, give me one. And then once we establish the relationship between x and x1, which is a parent-child relationship, and similarly, find out that y1 is y's, parent, then we can now go to the recursive definition, which basically says, we need to now confirm that x1 and y1 are second cousins, or z minus 1 cousin, but that does not work, okay? So what you need to do is to borrow something that we learned from the factorial program, okay? Which means, we have to introduce z1, and we say z1 is z minus 1. Because that was also in the factorial program, how we can make a new existential variable that is based on, one of the parameters that we are given with. So now, So instead of using z minus 1, we just use z1. And that's the recursive version. Now, if you only have the recursive version, it's not going to work, because at some point you will have negative z's, right? z1 will become 0, -1, -2. Then it doesn't make sense anymore, right? So it has to stop at some point. So you have to think about the base case. So in this sense, it is really kind of similar to proof by induction, except I'm working with the induction step first. Then I get back and go like, okay, what is my base case? So you needed to stop. at some point. And the way that I make it work, or the way that I make it stop, is to use 0. Now you can use 1 if you want to, but I think 0 is more general. In other words, 0th cousin, okay, as opposed to first cousin, is a sibling. That's basically what it is. So the way we define that is relatively easy. So we basically have to say, find me a parent x1 of x, but we also have to make sure that this is the same parent of y. So we have x1, y, and there's one more, because we have to make sure that x and y are not the same. If I do not check and make sure that x and y are not the same, then we end up with a problem, because then a person is its own sibling. And sibling is not, huh? Sorry? Negative first cousin. So that would not work. So we have to make sure they are not the same, which also is telling you that cousins as a relation is not reflexive. One is not one's own cousin. Okay? So we have to now express that. There are two ways to express it. Last time, I think I'm pretty sure that we talked about this as the negation, and then you have to use equal equal to basically say they are not the same. So you have to add the last one, because otherwise you end up with a lot of people who are not really cousins, but it will show that those people are in fact cousins. So are we okay so far? Okay. But you can see how this is it. All the rules that I need to set up are here. The rest is really just giving ourselves all the parent of stuff, okay, to test it. So I got the whole thing set up already on. Huh? Oh. Oh, okay. Thank you. There we go. Thanks. So are we okay with this definition, or do we have any? Do you want me to discuss this a little more? Okay. All right. So given these are the rules, now we can test it. So the way I did it was to use the web interface of Prolog, which is really handy. I did kind of like the minimal work to test it. So I just have A having offsprings B and C, X has offsprings Y and Z, and then K is the grandparent having offsprings of A and X. So this doesn't fulfill all the requirements of the homework assignment, because you have to work all the way up to second cousins. This will only work up to first cousins. But it will still test the program, because it will test both the sibling part as well as the cousin part. And because of the recursive relationship, if we can see that first cousin is working by using the recursive definition, I'm pretty sure the second cousin will also be working. Is that okay? So the way I tested this program, you can actually see how I tested the program here, is for this one, I'm looking for all the cousins of B, okay? And I did not follow my own rules either. This is singular cousin instead of cousins. So other than that, the logic is the same. So this will try to find all the cousins of B. So instead of just running it to find out, we want to look at this and figure out, okay, who is a cousin of B? B is a sibling of C, but I'm looking for first cousins, so C should not be a part of the answer, okay? But at the same time, Y and Z should be the first cousins. A and X are not first cousins, because A is a parent of B, and then X is basically either an uncle or aunt of B. So those would not qualify as answers. So in this case, the correct answer would be Y and Z. So now we can test the code using this web interface. So just click that, and you click next, so it gives you all the answers. And it does show that Y and Z are both cousins of B. So that's kind of how it works. Do we have any questions about this? Yes, go ahead. Mm-hmm. Okay. Okay. I will check it. Okay. Any other questions? Yep. Yes. Well, the code is actually right here. So it doesn't show very well because it has to wrap around.
Do we need to say z should be higher than 0, or we don't
That's an interesting question. Okay, so if you do not specify that z has to be greater than 0, then um, if you specify -1, then it will go negative. It will keep going, and it's not going to work.
oh, okay.
Yeah, I can show you what I mean by that. So if you give it a -1 to begin with,
Okay.
it will never solve the whole thing, because if you give it a question like that, then it will try to match the first rule, but it won't match the first rule because -1 and 0, they cannot what is the word, unify. They can one cannot substitute the other one because they're both atoms and they're different. So now it will try to unify with the second rule, which it will, right? Because z is just a variable which can be which can bind to any atom, which is -1 is an atom. So we'll go through this, figure out what is z1 being uh, -2 in this case, and then we'll try to resolve this one. So it will keep doing that, but it will not find an answer because at some point the parenthood will run out. So it's going to return false, and then after that the whole thing is going to be false. So so this is my conjecture. My conjecture is if you do a query like that, it will come back with just false. Okay? So we'll check it out. See if tag can really think like a computer, right? It is a gift. That gifted child who's more like a robot, right? So are we good so far with this? Yep.
I think you already mentioned it last time, but why can't we just put z minus 1? Like, why do we need the z1 again?
Why do we need a?
The z1 for the recursive thing?
It's just a syntax of Prolog. You cannot put an expression in a subquery,
Okay.
and that's it. I mean, there's no other really particularly good reason, and it has to do with how it performs the substitution, because because the substitution has to be from either an atom or a variable, cannot be from an expression. Yep.
Would it be acceptable if you actually just defined a first cousin and then defined a second cousin? Like
Then.
hard coding, like
Mm-hmm.
like you would hard
Then you
code.
will lose some points because I think in class I did say that we want this to be as general as possible. Yep. And I'm pretty sure I used the word recursively in class too.
Yes.
Yep.
I mean, you could still define your second cousin recursively, right? I'm pretty sure that's how I did it. It was still recursive, but I'm hard coding the value 2.
And the value of 1.
Yeah.
So it would only take you like a minor modification to make that work. Now, if you define other rules to define like grandparent and grand-grandparent, and then make use of those in the second cousin one, then it's not going to be recursive anymore.
Even if I use my first definition of cousin within the second cousin definition.
But we also have to make sure that there are no other dependency that is not recursive. Because if you use grandparents in the second cousin definition, then that is not recursive, right? Because you're not defining, because you're not, how should we, parameterizing grandparent with a number indicating how many levels of ancestry you're talking about. All right. So are there any questions? Any other questions? Yep. Mm-hmm.
Would there be a problem with using uncle?
Using what?
Uncle instead of parent sibling?
Nope. I don't have a problem with that as long as it is a recursive definition and it works in general. Yep. But the way I came up with this one was really just by reading the definition that we found and parameterizing, the third with a number, and then the second with that number minus one. That's all I did.
I did the same thing, but if you
Mm-hmm.
Google just regular cousin,
Uh huh.
it says the child of one's uncle.
Uh huh. Okay.
So that's where I got my recursive
Got you.
definition from.
Yep. Yeah, I looked up that one too, but then it doesn't have a number. Uncle does not have a numerical value associated with it. So I just go like, okay, let's look up second cousin. And then third cousin is the best definition because it has third and second in it. So one is z and the other one is z minus one basically. So that's how I just go like, okay, this is an easy one to implement. So are we okay with all of these, with this particular homework assignment? Was it fun or was it kind of like not fun? It was kind of fun, right? Hmm? Oh, okay. Yep. The code, sure. There we go. Mm, no, because it's trying to find out whether cousin B has any cousins, but because of the negative one, eventually it's going to run out of parenthood, so it will start to fail, these two, predicates, and if these two are failing, then there's no way to check the rest, and then it would just kind of go back and say, because we have these two as well in the recursive one. Now, this is what you can do to turn this into infinite recursion. All you have to do is to move this part ahead of the parents of. Then it becomes infinitely recursive. Do you see what I mean? Okay, let me just do that. Okay, so you can actually, huh? It would not fail out. It would just go on and on and on forever. Okay, so I'm gonna take this, okay, and cut it, and then do this first, and then do that. Now, when you think about this from the perspective of Boolean algebra, what I did should be okay because conjunction is commutative. Okay, A and B and A are the same thing, right? I mean, you should be able to move it around. But this is going to be a big problem for this program because the first thing it's going to do, for this particular query, b, y, and negative 1, is, okay, it does match this. Okay, x is b, y is still y, and then z is negative 1. Not a problem, right? So this rule will, quote unquote, fire. When the rule fires, then it would evaluate things in this particular order. So the first thing is, okay, what is z1 going to be when it is supposed to be z minus 1? Oh, that's easy. Z is negative 1. Negative 1 minus 1 is negative 2. So now we know z1 is negative 2. Not a problem. Then we'll go here and go like, okay, find me, it would say, find me x1, y1, and negative 2 here. Find me a, let's see, first, second. How do you say negative 2 as a quote unquote second? Okay, that's first, right? First is 1. Okay, what is negative 1? Negative first? Negative first. So find me the negative second cousin. Find me a pair of negative cousins first. Then I will confirm that they one is parent of x and the other one is parent of y. What is that going to do? It goes back and try to match this rule. Does not match because we have a negative 2 instead of a 0. Then they get back here. Then we'll try to look up negative third cousins, negative fourth cousins, and we'll keep going until the stack runs out. Well, since it's not my computer, let's give it a try. Yep. Yep. Stack limit exceeded. I can, in fact, think like a computer. Let's see here. 1, 2, 3. Yeah, 2 million something. Yep.
So is there a way we could try and make it a tail call so it doesn't run out of
Well, that's what we had earlier was to invert the order of the parent of versus the cousin thing. Yep. So if I flip the order back to where it was,
You just control Z.
hmm, does it work? Oh yeah, cool.
If we take the base case
There we
out,
go.
will it?
Hmm?
If we take the base case out, will it just keep going without running out of?
If we take out the base case,
Yeah. If it has no base case hit, so shouldn't it just reverse like?
okay, that's a good question too. Okay, so let me just kind of relay that question. So the next question is, okay, if that is screwing up things, what if we move the first rule down here instead? So we're just reversing the rules and see what's gonna happen. Okay, so let's give it a try. I don't think it's gonna matter in this particular case. Okay, so we take this and then we put it after here. So in this case, because we are changing the ordering of the rules, alternative rules are automatically connected by a OR. In other words, it will try the first one. If the first one fails, and it will try the second one. And if that fails, it will try the third one, and so on. So in this particular case, it will still say b is bound, or x is bound to b, y is still a variable y, z is bound to the value of -1. Okay? Then it will go find, give me a parent of x, or b in this case, and then it will say, okay, we'll find any parenthood in this case. One will bind to y1, the other one will bind to y. Okay? It doesn't have a problem with doing that, right? And then it will go to this part here and say, okay, now -1 becomes -2, as z1. Now we're trying to find x1, which should be bound to something, y1 should be bound to something, and then z1 over here is -2. So it doesn't match this one, it will go back to here. So at some point we're going to run out of parent of, because parent of is not cyclic. So once you track down one particular parent of a relationship, eventually it will run out, because eventually it gets to parent, it will get to grandpa or grandma K, and then it's going to stop, because that atom has no parent in the database here. Okay, so in this case, it's not going to matter. It will still return false. Okay, or at least I think it's still going to return false. Let's try it. Yep, it just returns false without taking really a whole lot of time. But it will have an effect when we are actually working. It's supposed to be working. In other words, if you try to say, give me all the first cousins of b, which we did earlier, and it was successful, now it would not be successful anymore. It would just come back with a fail, or false, because it doesn't know when to stop and say, oh yeah, this works. Okay, now go back and tell the earlier invocations that we got true, and then it back propagates the whole way. So in this case, it's not going to go into an infinite recursion, and the reason why it cannot get into an infinite recursion is you eventually run out of parenthood in the family tree. But it will do something incorrectly. It will come back with a false, which basically means b has no cousins. But that is not true, because b does have 2 cousins. So let's run it. Oh, it does. Yeah. Okay, next.
It's like a disjunction. Doesn't it just check the recursive one until it fails and then defaults to the other one?
Oh, yes, because if one fails, it will go to the other one. So it will still fire the other rule when xy0 does not. If you have xy being something and z being 0, if this fails, it will still try the second one. Okay, you're right. Okay. So after all, I cannot really think like a computer. Not all the time.
Prolog is kind of different.
Hmm?
Prolog seemed kind of different. Like
Mhm.
a lot of the logic that my brain uses for like C++
Mhm.
C didn't quite like transfer over, because I would try to do
Right.
something and then I'd get an error and it'd be like, it's not a function. Can't do that.
It is a predicate is really not a function, because the mechanism of backtracking is built into Prolog itself. If something fails in a conjunction, it knows that, okay, let's go back one step, try something differently, and go forward again. Which is great in a way, if you're looking for an answer, but it's also different from what you're used to in C and C++. Yep. So are we good with this? Yes? Okay, that's cool. Okay, so just as an example, it just occurred in my mind like 2 seconds ago. Um, can you think of a way to define a maze using rules like this, and then write an algorithm to find a path from one particular cell as a coordinate or as a number to another cell in a maze? And if that is possible, how would you do it? I'm giving you guys more exercise or more practice to make use of Prolog. Okay? Okay.
Well,
So
it's essentially kind of a tree already. And a tree, in a sense, is kind of like
it's not necessarily a tree, it is a graph. Okay? Hmm?
Every combination, like every, if you're at a node, check every node, and then on those nodes, check every node until you eventually hit the end, and then you find the path, right?
Well, let's look into the representation first. So this is interesting because it relates Prolog to graphs. Okay, so let's go ahead and get started with this one because we want Zerno. Yeah, there we go. Okay, control equal. There we go. So let's go ahead and look at a very small, two-dimensional square maze. Okay. So the outside is closed, and it's a 4x4, maze. So we'll have, I'll just call these cells 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. Then we'll try to have some partitions, so we can now say we have a partition here, like so, and something like that. Make this a dead end. Do something like this. Okay. Okay, so now it's a maze. Are we doing okay so far, of how I just made a maze here? Okay. And we can use one more, because 5 and 6, they can be connected like that. It's not wide open. So if my question is, how do I go from cell 2 to cell 16? Okay, you guys can solve the problem like right away because it's all visual, right? Because you can say, oh, okay, 2, 3, 7, 11, 10, 14, 15, 16. Now we are at 16. Okay, that's how we solve the maze. But the first question is, how do we represent this maze using Prolog?
Is touching relationship, so 2 is touching.
Adjacency, right? So whether, but you also need to know the direction of the adjacency. Well, I guess direction is not really needed. You just need to express as adjacency. So how do we express adjacency in this case? Yep. So you just say adjacent. 1 is adjacent to 5. Period. Okay? It's not a general rule. It is just, you're just asserting that 1 and 5 are connected to each other. So now you have ADJ. Okay, I'm just giving you another example. 5, 6. So you have a whole bunch of adjacency, blah, 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 like that. Then you go like, well, but that means, we can only go from 1 to 5, but not 5 back to 1. And I don't really feel like, writing the other half of the adjacency, like adjacent 5, 1, adjacent 6, 5, and so on, because that's a lot of chore. Yep.
you can just write a rule for like you can call it adjacent to, where it's x y, and then you have a little turnstile thing, the colon line, and then adjacent y x.
Yep. That's it. Mm-hmm.
So if we wanted to like find a path from like 1 to 16, wouldn't we have to know how to like specify collections of like atoms or something?
Nope, you do not. Okay, so are we doing okay so far with the expression of the problem itself? How do we represent the problem? This is a maze. This cell connects to that cell. This cell connects to that cell. So that means that when we have a wall, Okay, like in this case, 9 and 13, they're not connected to the other cells. It's just the lack of adjacency. Is that okay? So 9 has an adjacent to 13, and then because of this particular rule here, we don't have to specify 13 is adjacent to 9 because having expressed one is automatically having expressed the other one. Is that okay? So now the question is, how do I go from find a path from 2 to 16? Let's just say that we don't need to find the shortest one. We just need to find one. Okay? How do we do that? We're basically asking, is something reachable from something else? That's basically what we are asking. Okay? So how do we express that? Yep.
We use like a similar kind of recursive thing and then have the like base case be adjacent to the destination.
So a cell is always adjacent to itself, right? That's when we can stop. Okay? Or it's, I should say, connected to itself. Okay? It's reachable to itself. So now we define reachable. Okay, reachable. And then we say X is always reachable from itself. Okay, so any cell is always reachable from itself. Okay, that's the base case. So now what else do we express? So we have reachable again. Okay, reachable. And this time we have XY. And this time we have to use the recursive definition. So X and Y are reachable if there's a Z in between. X is already known to be reachable to Z, and then Z is adjacent to Y.
We just want it to be basically transitivity, just
Sort of like that. Yeah, so we basically say adjacent XZ and reachable ZY. Then we can determine reachability. Now, does it necessarily find you the shortest path? No, it will find you a path, which is not necessarily the shortest one, but it will find one at least. Yep.
wouldn't it not find the path? Doesn't it just tell you if there is a path?
It will tell you whether there is a path, but it won't print the path out. Okay, that's a good question. Let me hear that question first, and then we'll get back to that one. Yes.
So Z is specifying there's multiple atoms between X and Y?
Z is existential. Remember, any variable that is on the right-hand side of a rule only are existential only. Anything that is specified on the left-hand side are universally specified. In other words, I'm just saying, can we find at least one Z so that X is adjacent, directly right next to Z? And on top of that, we can also somehow prove that Z is reachable from Y.
But in that condition, don't we need a adjacent ZY as well?
Nope. We don't need that. Because everything eventually boils down to reachable of a cell back to itself. Okay, so let's think about a very simple case, okay? Let's say we just ask, is 2 and 3 reachable? So we say reachable 2, 3, okay? What's going to happen? Would the first rule return true? The first rule would not return true because if I substitute X with 2, then it's not going to work. It doesn't match, okay? So it has to fire the second rule. So when we fire the second rule, X would be 2, Y would be 3, right? And then we ask, is X adjacent to something so that something is adjacent to Y, okay? So we look up the list and go like, okay, can we find that 2 is adjacent to 3? Yes, okay, we found along here, 2 is adjacent to 3. So that would bind Z to 3. Is that okay? So when Z is 3 and we know Y is also 3, right? Then we'll fire, this is a conjunction. So now it will evaluate reachable 3, 3. Then it goes all the way back to the beginning, log down all the rules and find that, okay, the first one we see is reachable XX. Well, X is 3, X is 3, it fires, okay, returns true. then we get back to this part here and say that yes, cell 3 is in fact reachable from cell 3. Okay, go back to once, and then the whole thing becomes true. Is that okay? Does that kind of illustrate how it works a little bit? Do you guys want to put this into Prolog and actually see it work? Or do you want to use this particular maze or use a simplified one? I don't care either one, either way. We can use this one, I suppose. All right, so let's see, how do I start a new program in this interface? I have not used it.
On the,
Huh?
if you look at the top word,
Next to where it
Just-
says program.
down a little bit, where you right clicked.
Left.
Yeah, to the left.
To the left. Hmm?
Top left.
Top left.
Next to where it says program.
It's underneath where you right clicked.
Oh, okay, gotcha.
The plus.
Okay,
Over.
make a new tab. There we go. Okay, so under the new tab, we want to create a new program. There we go. Okay, thank you. I know how to do this. See? 1 5 5 6.
610.
Mm-hmm. And 10 has a few adjacencies. 10, 14. Now we have to choose which way to follow first. Okay, fine, we'll do that first.
7.
Uh, 14, comma 15. 16 to 12. And 12 back to 8. And then the isolated 9 and 13. Those two they're still adjacent to each other, because if the question is 9 reachable from 13, I still want to be able to answer that one, even though they're isolated from the rest.
You need one more.
And then we want the there we go. Okay, so now we have expressed the graph itself. Yep.
Have you been recording?
I believe so. Pretty sure about that. Yep, it's recording. Yep.
Just checking.
It's good to check. Thank you. I'm not complaining. I'm simply saying that, yeah, I thought so, but let's check. Okay, so now we can specify the rules, reachability rules. And we basically say reachable XX, and we just give it a period. Now, if you really want to say it is true that X is always connected to X, you can redundantly say that. It's fine, okay? It's just not needed. Is that okay? So that's just doing the same thing as without the colon dash, but if you want it to be kind of looking more complete, you can do it that way. So now we have XY only if adjacent XZ, find me a Z that X is right next to, and on top of that, can you check whether Z and Y are reachable? That's it. Okay? Are we doing okay so far with this? So now we can ask some queries. Okay. All right. So what do you want to do? Okay, let's do the one that we worked on earlier, okay? So the one that we did earlier is 2 to 16, right? So let's check that. Okay, go back to the browser, and we say reachable is 2 and 16 reachable from each other. Okay, the period is actually not needed. We just click run. Uh, I think it has to do with the adjacency. The adjacency, is not working because it's endlessly recursing. Yep. Okay, so we have to somehow fix that problem. Okay, does everybody see why the adjacency itself is a problem? Okay, so let's go ahead and just give it a adjacency test first. Okay, so we'll just ask a particular adjacency that does not exist. So we say ADJ 9 because we know 9 and 13 are outside, right? They're disconnected from the rest. This is going to cause a problem. I mean, click.
Is it gonna keep looping?
Yep, because it will check whether 1, 9 are connected, are adjacent. Then it will go back and check 9, 1 is adjacent, and so on. Yep.
So like, even if we replace that predicate, that adjacent xy, adjacent yx thing, if we even replace that with like hard coding that, won't we still run into the same problem? Because you would have like,
Mm-hmm.
it's 3 reachable from 4. Oh, it's 4 reachable from 3. Like,
Mm-hmm. So there's one way to fix this problem. It's not a difficult fix. It's a relatively simple fix. So what we do instead is we get rid of this particular adjacency definition. Huh?
it is still better. It'll find it eventually.
Because it's a tail end recursion, so it does not use the stack. So it becomes just a really infinite loop in this case. Because tail end recursion means that you can turn it into a loop. There's nothing to go back, then continue, so you don't need a stack to do it. So we can go ahead and try to stop it. Hmm? Abort.
Right underneath it.
Oh, okay. It's right next to it. Apparently, I'm not the only one who needs to stop a program that has run away. Okay, so to change this, we just have to say next to. Okay, I'll define next to. So x is next to y only if x is adjacent to y, oops, or y is adjacent to x. Right? Then the rest of the program is going to make use of next to. Is x next to y? I think that will solve the problem. Okay, so just to test it again, so we say next to 9, 1, and it should return false right away. Yep, there we go. So now we can ask more difficult questions, which is reachability. So is 2, 16 reachable from each other? And it should return true. No, no.
Shouldn't it just still be doing the same thing? Like,
I know what it is because reachability can go back and forth too, and it just endlessly goes back and forth. Because it because it knows how to make a next step, but the next step can go back one step too, so it can basically just alternate between two steps. So now we have to prevent it from alternating between two steps, so it cannot get back. So we have to get into lists. Okay, so we're not going to do it. Because we have to keep track of what we have visited already. And if you're trying to go back to one thing that we have already visited, we have to say, nope, not going to go that route.
Can you just say, when you're doing the reachable, can you just say x not equal to y? There?
But that will only prevent,
Going
okay,
back to the one you just did.
here,
like if they're not the same.
x has to be different from y.
Yeah. Well, I guess it doesn't. That's
Well, then
not
once
really
you
the
reverse
case.
once, it doesn't have to be different anymore.
But it won't stop a loop though, because if you actually have a loop, like involving like 4 different cells, it was then you have to like express a cannot be b, cannot be c, cannot be d. So you cannot scale that up. So the only way to scale up is to use a list to keep track of what you have seen already, and then if you are going to a cell that you have visited already, immediately return false and go back. Yep.
So based on this, what kind of questions can we expect on the final since we did like the fire exam test?
So So this is a particularly kind of difficult question because we have to look for things that we have seen already, and we have not talked about lists yet in this class. So there's no way I can actually ask this one as a question in the final exam. But I can, yeah, go ahead. Yeah. So I can extend on the homework and say, okay, if we associate genders to atoms with the cousins homework assignment, how do you define grandmother? Right? I mean, that would be a very simple one, but I'm thinking, but I'm talking about as an example. So, yep.
Do you think it's going to require any like other syntax beyond what we've done in our homework?
No. So the final exam, will not involve any syntax or constructs that we have not yet, encountered. So if you look at my solution to the cousins program, the factorial program, and there was one more that I presented. Oh, the Jedi one. The Jedi one is actually in my notes. So all of those, it will give you, all the pieces that you need to understand for the final exam. Is that okay? All right.
Or we could print out, right?
Hmm?
List of all the syntax. I mean, it's open book, so print it out.
Yes, absolutely. You can even go to the Prolog, the SWI Prolog website, and download certain pages. You wouldn't need the entire thing because that's really long and it would just be confusing. So you just need to know what is a comma, what is the colon dash. What does it mean? What is a backslash plus? That you also need because you need negation. Yeah, that's about all that you need in terms of syntax, because we are not dealing with lists, which is a kind of a good portion of how things can be a little bit more complex. So are we okay with this example? So we can represent it, but the expression of a solution is not that easy. Yeah, because we'll need the representation of a list to keep track of what we have seen, so we can avoid loops. Yep.
So if we had like an actual just plain directed, not bidirectional graph, would it work?
Yes. If you have a directed graph that has no loop, which means it is just a tree, then it will definitely work. Huh? The A-star algorithm still requires the construct of a collection, because you have A-star has O as a set, and then Dijkstra's has Q as a set. And since we have not talked about a list, there's no way you can actually represent a set in Prolog. So we cannot express that solution in Prolog because of that. Yep. So the lack of a collection concept is really a big hindrance when it comes to expressing algorithms. So are we okay so far? Do you guys want to see how this program actually will work when there are no loops? Okay, so let's give it a try. All right, so in that case, we just have to go back to adjacency and not next to. So things can only go in one way but not backwards, right? So we can only express that. And next to is, even though it's defined, it's not used in any way. So now we have to be careful and find out whether 2 and 16, using a directed graph, concept, whether they're connected or not. So where is? So 2 is connected to 3. Oh, okay. So it's not going to work because the way we express the connectivity between 2 and 3, 2 has no outgoing edges. That's right. But using only what we already have, let's see.
You might be able to go from 3 to 16.
Yeah, 3 to 16 should work because we have.
You go 3 to 4.
Uh-huh.
And then 4 is a new 4 to 5.
We don't have 4 to 5. Okay, I'm more thinking about from 1 to 1 to 16 will work. Yeah, 1 to 16 will work. Okay, so we'll work on this mentally first. 1 connects to 5, 5 goes to 6, 6 goes to 10, 10 goes to 11, 10 also goes to 14, 14 goes to 15, 15 goes to 16, and there are no loops in this particular case, I think. Yep, because we did not express two edges to go to the same thing. And if we look at the graphical representation, where is it? Here. Okay, so we are looking at 1 to 16, and you can see how that path itself does not involve any loop, so I think that will work. It can go to the wrong path. Yeah, but it'll always backtrack. Yep.
But is there like a print as a side effect kind of statement that we could use to print Z as we go?
Yes, there's a way to do it, but I cannot remember, so I'll Google it. So we'll Google SWI prolog print. Okay. Should be a pretty simple thing. Print just takes one argument, and that's all. Print a term for debugging purposes. Okay, sure. All right, so we go back to the program and do some printing. So what do you want to print? Don't you want to print x2?
Wouldn't it print X every time? Well, I guess that'd be good though.
Hmm?
Print a new X.
We'll print both of them. Okay, it's complaints. No permission to call sandbox. Hmm? Well, then we ask Google some more things then. Huh? Hmm? Right term.
Oh yeah, that's what I meant.
Hmm? Say that one more time.
I meant WRITE, right?
Okay.
Yeah.
Okay. So instead of print. Okay. Print term to stream. And if it is right, what does it do? Writes term to stream. Okay, well, yep, same thing.
Oh yeah, okay. So is it like
It could not open a stream, basically. That's what it's complaining about. And I think it might be specific to the web interface.
Try doing it with one argument.
Hmm?
Try doing print with one argument.
I don't think the number of argument is the issue, but
just copy and paste that locally?
oh. Oh, because the second argument is the stream, or one of them is interpreted as a stream. Yep, there we go.
Distinguish between like single numbers and
And having a line feed can be helpful. Huh? Yeah.
Yeah, but it printed every one that it tried, so it also went into like 11.7.
Yes. It went wrong. It went off to the wrong path, and then they backtracked.
So
Hmm?
that time it found it.
Yep.
It went to 5, 1 to 5 to 6 to 10 to 11 to 7 to 3 to 3 to
Do it
10.
again.
Mm-hmm. Yep. It backtracked at some point. All right.
What if you have it write Z? Would it just print the same?
If you write Z, well, okay, you can do it this way. You can say would that work? No, it won't. It won't work entirely.
could you have the write be after the recursion so that it like prints it only if it succeeds? Or no, it would still end up hitting that.
Well, it is still going to okay, I see what you mean. So you want to do it
I don't think it'll work.
after this, right?
Because things isn't just
Okay, but what do you want to print?
Print Z.
Okay.
be cool with that.
Yeah, this will work.
Wouldn't you wanna?
This should work
Yeah. Okay.
because it has to Because in order to get to this z, it has to be reachable here first, which has its own right? So basically, it will print out everything along the whole path. Because if something is not successful, it will not get to the print. It will not get to the right. So, yep. So it went to from 1 to 6. Well, without the line feed, it's a little hard to.
Yeah, no, I think it goes from 16
Can you
to
put
15
space
to
in
14 to 10 to
Oh,
6
so it's
to
just
5.
backwards.
Okay.
Right, so it goes from 1 to 5 to 6 to 10 to 14 to 15 to 16, and that's the path.
Right, and then 1 is not printed because it is X. We only printed Z.
Can you have white space between them?
I think we can do that.
Right link.
Well, you can always cheat and
If you do right line, it'll separate that line.
a right line. Okay. Okay. That's interesting. Right line is copied from Pascal. That's a Pascal name for writing something with a line feed. There you go.
Wow,
Yep.
much easier.
Because it's backtracking. Yep.
You always know where you started because it prints the initial predicate.
Hmm?
You always know which one you started at because it prints reachable 1 to 16, so you know which one the last one is 1.
Mm-hmm. Yep. All right. It is. But it doesn't deal with loops. So to deal with loops, we'll need a list concept.
So, but if you wanted to make a bar graph without a loop, couldn't you have the hard-coded double-sided edges?
If you want a bigraph,
Right. So if you were just willing to copy-paste all the adjacency
uh-huh,
declarations and reverse them all yourself,
then you have loops. It won't work with loops at all.
that creates a loop, doesn't it?
Huh?
That would create a loop.
Yes, because if one is adjacent to B, if one is adjacent to 3 and 3 is adjacent to 1, then you already have a tight loop there. And it cannot detect that there's a loop. So the problem is it cannot detect it's in a loop, and it will keep going, going back and forth between those two until it runs out of stack space. So you need a loop detection, but loop detection means that you will need to keep track of a list of things that you have seen already, which we have not talked about. So, and this is a little bit too late to introduce, the concept of a list in Prolog. Yep.
Could you, okay, so could you have 3 reachable functions? So one, say you swapped the argument 16 and 1, would it still work in this case? It wouldn't, right? Because
It would not, because it can only follow the links forward and not backwards.
So what if you had well, okay, that would just give you another loop, right? If
Mm-hmm.
you had a second reachable that was yx.
Right. It would just because in terms of concept, you're still just you're implementing something equivalent to the first program had, except it's expressed differently.
Right.
Yep. So to get this program to work in order to find a path in a graph that has loops, you really need to understand what the program needs to be able to detect that it's in a loop. And upon the first detection of a loop, it just backs off. All right. Any other questions? So did anyone end up with a problem of loops, in the ancestry problem?
I feel like I might have. Because it didn't run out of stack space. It just printed every possible answer twice.
That is because you did not. No, it's not. Well, okay, you might have 2 parents, but the cousins from each side of the parent should not overlap, except for very few strange cases. Yeah, because if you think about it, okay, so you have your dad's side, cousins, and you have your mom's side cousins, right? Do they overlap?
It should.
In most cases, they do not, right? Because unless your dad and mom are related, then you can have cousins that are overlapping.
So I copied the pre-morphology family tree with all the parents.
That would be bad. That then we'll end up with a lot of duplicates. Yes. Or if you use time travel, so in which movie did one person was become his own ancestor?
That was. I know Futurama.
Futurama? I think it's Futurama. That's right. Yep.
Bryce's own uncle.
Yep. So in that case, you end up with a loop, which is not good in a program like that. So are we doing okay with all this stuff? Okay. Any other questions you guys want me to kind of answer or review for the final exam? Yep.
Will you be uploading the previous finals and answers?
Okay. I thought we did that.
We did, but you didn't upload the file.
Oh, okay. So to upload the file, I can do that. And we'll just add it to the collection of final exam already at the end here. So we'll upload a file. It's a new file. And we are looking at okay, we'll choose one of these. We'll choose this one. Yep. There we go. So you got it. I think the explanation of that exam, of the answer to that exam is already on YouTube. You have to look up the December 2018 stuff, it's already there. Yep.
And will you be able to rate our labs 45 as well?
Mm, I'll give it a try, but yeah. Yep.
For the dexterous homework, I found it really helpful following you go through the algorithm. Would you be able to do that with the A-star as well?
To go through the algorithm?
Yeah, like where you followed it on your spreadsheet. So I found it like pretty helpful to like.
Okay. Did we do that with A star?
Yeah, if you did it in a previous class and just watched that.
Oh, okay, I see.
I think he did it once.
Hmm?
He did it once.
I did it once. Okay. Yep.
Did you have an answer key in your shared folder for the fall 2017?
No, but if you look up YouTube, I think there's an explanation of all those answers. So let me check that.
I found the spring 2018.
Okay. So we'll go to YouTube, and I think you have to look up like kind of earlier, like 2018, December something. Hmm?
I found the dates in the
A
website.
playlist.
Greatest hits.
Okay, so we're getting close. We're getting warm here. 440 final exam Q1. There we go. So just look up all the ethics Q1 of cisp 440, and you should find the each one, being explained in its own video. So let me try that first. FXQ2. Yep, there we go. FXQ3. Yeah, so I think each one has its own video explaining its own answer. So you just have to look up, do a search, on YouTube, and that should find, all the answers with explanation. Yes, so recording my videos actually pays off because now I don't have to go through that again. But is that okay? Does everybody understand how to get to the explanation of the solution to the final exam in fall 2018? All right. Any other questions? I hate to let you guys go a little early, huh?
You have the final grade?
No. Yep.
You still have office hours this Friday, right?
Yes. So my office hours, I still have office hours, and let me go retrieve my office hours so that you guys can actually see it. So go to my Outlook, sent items. And then we go to this one, final schedule. Okay, so this is my final schedule. Tomorrow and day after tomorrow, my office hours are from 8 to 9. And then on Monday, we have our exam at 12:40, 11, 12:45, and then the office hour is from 10 to 11. But I'll be pretty much on campus, between the first final exam and the second final exam. So unless there's something that I have to take care of, I'll be on campus pretty much the whole time. So
On Friday, 8 to 9 for sure.
right. So for whatever reason, if you cannot make it to my office hour, you can send me an email and ask for another time to meet with you if you need to. You know. So is that okay? Any other questions?
If I heard you correctly on Monday, you said that time complexity would not be on the final.
Correct. Time complexity is not going to be in the final exam. Okay. Any other questions?
Big O notation time.
Hmm?
Like big O and then
Right. That's time complexity. Yep. Hmm?
He said time is complex.
Time is complex. Well, that is actually interesting way of looking at time because we see time as linear, but as soon as you turn time into a complex number, then time is now two-dimensional because you have the real and the imaginary part of time. Yes.
Can you just put a throwaway question on the test? It's like, what's big O? That's what you said.
Extra credit question for Big O for time complexity. No, that's not a bad idea. So that one is definitely marked as extra credit, which means you can just automatically not answer that question. I'll consider that. Which means if you don't want to study for time complexity, you can still get 100% out of the final exam because that question is optional. But if you do study for time complexity, then you can potentially get more than 100%. Then we consider like extra credit for the rest of the stuff. Would that work out? I mean, does anyone object to that idea? Yeah? Why are you objecting?
No, she's.
Oh, okay. Because the question was, is anyone objecting to the idea? And then Giselle said, yeah. So I don't have any objections, correct? Okay. Yes. I don't know how I'm going to ask that question yet, so it will be very difficult for me to give you a sample question at this point. But it will be something like I'll give you an algorithm, and I'll ask you about the time complexity. Okay, and I will ask you to show that this is the upper bound, and it's the same thing for the lower bound, and therefore it is the tight bound, or something along that line. You probably want to bring a piece of paper with all the definitions of the terms, or just print the modules and highlight certain portions of it. So because you need to have the terms with you, the definitions with you, in order to answer the questions. So I would definitely bring the print out of that module. If you decide not to answer the question, that's fine. But if you choose to answer the question, I think the definitions may come in handy. Okay. Any other questions? No other questions? Is anyone going to object if we end the class 10 minutes earlier? This is the only time of the entire semester that we end the class a little bit early. It gives you 10 more minutes. Yes, absolutely. All right. Well, I'm going to stop the class right now. And if you need to talk to me, just come to my office hours. If you cannot make it to the office hours, send me an email so we can arrange a time to do that. Yep. See you next week.